Okay, so this time we're going to imagine a car going around a track, but this track is not flat. This track is actually banked, so you can go around on a bank like a NASCAR track. But we're going to pretend there's no friction here at all. So that'll be interesting. So we're going to do like a cross section of this track right here. So what we're going to have is we're going to have a a ramp. And here's the car, here's the wheels, and then here's the car, here's the headlights or something. It's coming like at us. Okay, so we can draw an FBD of this, and, there's always this force, which is mg cosine of theta, and then there's a normal force going this way, okay? And then always down is mg sine of theta. Now, if we're going to see how fast this car need to go before it would fly up off the edge of the track, and if it does that, you generally would have friction going down, but we're saying this is frictionless, so I don't actually have to worry about the friction. I'm not going to draw it in there, and because I don't have to worry about the friction, I don't actually have to worry about Fn, right? Because friction is Fn times mu. So I don't really need to worry about what Fn is here. So there is a net force on this vehicle, and that's obvious from what we're doing, because it's anything goes around in a circle, there's automatically a net force, right? And the net force is in what direction? It's towards the center. So there is actually a net force. And normally don't draw the net force on the diagram, but I'm going to kind of sketch it in here to show you. There's a net force, from the car, pointing this way. That's FC. Okay? Now, how do we get that? Well, that's because there's this force going down, and this normal force here is actually bigger than this force right here. Okay? So there's some net force going, there's some net force kind of going up this way, and there's some net force going this way, and those two added together would give you this centripetal force right here. So I can actually sketch in, a force, parallel to this plane here. Like here's the inclined plane. Okay, so this angle here is theta, right? Theta, and so that'd be this angle right here. Okay, now this component of this centripetal force right here is mg sine of theta. Okay, and then this force right here would actually be Fn minus mg cosine theta. Okay, so see, this Fn here is bigger than this. So I take this, subtract this, and that would give me this component right here. I don't really need that. I'm not going to even use that in this derivation. We'll use it in the next one. But this mg sine of theta is this component right here, the centripetal force working inwards right there. So what I want to use this side. I want to use this side here, this angle, and centripetal force. So that's how I can do it. I can do this side here. The adjacent side would be mg sine of theta, right, should equal fc times the cosine of theta. So I take the hypotenuse fc times the cosine of theta, should give me this adjacent side here, and the adjacent net force here is mg sine of theta. Okay, so I can derive here. I can do mg sine of theta would equal fc is mv squared over r cosine theta. Masses would cancel out. I could divide both sides by cosine, and you'd get what? You'd get a g sine over cosine is tangent theta. I can multiply the r over here also, and that would leave me with v squared, because if I divide this side over here by cosine, it's gonna cancel, right? Multiply the r over here. So I get v equals the square root of tangent of theta. So this is the critical velocity for a car to go around a banked ramp, a banked turn, if there's no friction at all. If there's no friction at all, it's a square root of GR tangent of the angle. So this is that's a critical velocity equation for no friction around a banked turn. And we'll just leave that one at that.